I am on the part in your notes dealing with the addition rules for probability. So let's start with some simple ones first. Now I'm going to kind of paraphrase all of the information right here into just a few sentences, and then I'm going to go through the examples here, so try to kind of go with me as you can. If you need to pause or stop or rewind or whatever, have someone go back to my computer and do that. Let's start with first rule number 1, dealing with what they like to call mutually exclusive events. Basically what this means is if they are mutually exclusive, which is this rule 1, is that this event A and event B have no overlap. Like this, I'm going to call this example 1 down here. There is no overlap in maintenance, production, office staff, and management, meaning there's nobody that has both of those things. So all of these things are mutually exclusive because there's no overlap. So if we want to find the probability a company has 66 employees, if one is chosen at random, what is the probability that a maintenance or a production worker is chosen? That's 2 events here. It's simply adding, which is kind of what we did yesterday when you had the 6 or the spades. When you drew a card, it could be a 6 or a spade, except now we have 2 events. So we have to talk about them both separately. So we're going to go the probability of a maintenance worker, and we have to add the probability of the second one is a production worker. So the probability of a maintenance worker is 14 out of the 66. And the probability of a production is 37 out of 66. And then I'm just going to add those things together. So I end up with a, what do we got, 61 out of 66? No, that's not right. Let's try 51. 51 out of 66. That's what I get for not having a calculator. And you can reduce that, get it into a percentage if you really want to. You don't have to. But if you did, it would be, looks like according to mine, it's be about 0.772 or 77%. So that is 2 mutually exclusive events. These next couple examples on the next page are identical to those. So what I want you to do is you should be able to do these on your own. What I will do is I'm going to pause the video. I'm going to write all of the answers, and then so they will just magically appear for you. But have someone go back to my computer and pause so that you can try these first. We'll go with these first 2, I believe, are mutually exclusive. Nope, I lied. Just the first one. Just this one right here. So try this first one. Have someone go pause the video and try that first one, please. With highlighted in green here, came out to a 26% or a 0.266. Either one is fine. So that is 2 mutually exclusive events, meaning there's no overlap. You were either Democrat or Republican or independent or American. Now this example down here, dealing with applying for a job, this one has some overlap. Because there are 20 men, 16 women, 8 of the men and 12 of the women have a PhD. So there are 2 events, meaning men and women, and then there's another event, which is a PhD, and there is some overlap, meaning some of these women also have a PhD and some do not. So we have to use the other formula back on this page, which I will quickly scroll down. We're looking right here. Mutually exclusive, meaning it has to be a woman and a PhD or a man and a PhD or no PhD. These are not mutually exclusive. So, going back up here, probability that one is chosen a woman or has a PhD. I'm going to take the probability, and please write this out because this is going to make more sense later. We're going to get some more complicated ones, but it's the probability of a woman plus the probability of a PhD minus the probability of both. So, probability of drawing a woman out of the first one is 16 out of 36. Plus the probability of a PhD, which there are 8 and 12, so there are 20 out of the 36. Minus what we like to, I'm going to call this the overlap. We're taking away women that have a PhD, which woman over here is 12. Of the women with a PhD of the total, which is the 36. So we have a 16 and a 20, which is 36, minus 12, or 36, which is 24 out of 36, which divide both of those, and by 6, 4, 6, you get, it looks like about a 2/3, or about a 66% chance. So please get used to, I'll get a highlighter here, please get used to kind of writing this out. This is going to help us quite a bit later. So I'm going to do the same thing on this next example, and then I'm going to have you try these percentages. If you want to work ahead, please do so. I'm right here. We're apparently at some sort of party, which, you know, as a stats party, I can only imagine how awesome that is. So there are 32 men, 16 of whom are without dates, and 28 women, 12 of whom are without dates. Find the probability of picking someone at random, getting a person who is a woman or without a date. So I'm going to go probability of a woman or no date is equal to the probability of a woman plus the probability of no date minus the overlap. So, first one is probability that you picked a woman. Says there are 32 men and 28 women. So there are 28 out of the total, what have we got? 60? Plus the probability of no date, which there are 16 and 12 that have no date right here, without dates and without dates. There are 16 and 12, so that is another 28 out of 60. Minus the overlap, which 28 of them, which is 12 are without dates. So here's where I'm getting the minus part. Minus, oops, not 28, my bad. The 12 that don't have dates, all over the total again, which is 60. Combine all those things together, 28 and 28 will give you a 54. No, 56, let's try. Minus the 12, all over 60. 56 minus 12 will get you to a 44. All over 60, reduce both of those. Divide by, what do we got? Divide by 2 will give you a 22 over 30. Divide by 2 again is 11 over 15. Same thing down here with percentages. If 47% of the people read a newspaper, 62% watch television, 25% do both, we're going to go the probability. Find the probability of picking a person at random who reads the newspaper or watches television. So we're going to go probability who reads the newspaper or the TV. It's the probability of the newspaper plus the probability of a TV minus the probability of both. I'm just going to write the word both. So now it's just working with percentages. It's a 47 plus a 62 minus 25. And grab a calculator, work that out. What do we got there? 109 minus 25. So 84. All right, you should be able to do that same thing with this example down here. I'm not going to go through that, but please pause the video a second and try that at your desk. Please try this example with dealing with 38% down here. What we're going to talk about is on this next page dealing with the multiplication rules for probability. This is where things get a little weird because we are going to start talking about dependent, try to highlight here, we're going to start talking about dependent and, scrolling down, independent events. Now the easiest way to describe these is simply if you have a dependent event, that means what you did on the first one affects what's going to happen on the second one. So it's kind of a way to reword this is, for example, if you draw a deck, if you have a deck of cards and you draw out of a deck of cards, you draw a, we'll say draw a 7. And you do not replace. If you do not replace this thing, that means you change the probability because now there's only 51 cards of the deck instead of 52. So therefore, a do not replace is a great example if you're drawing a deck of cards. Do not place is an example of a dependent event. An independent event would be like if you were to flip a coin. So if you were to flip a coin and then also you had, again, we'll go to our lovely example of you have a bag of marbles because everyone does. If you were to flip a coin and then also draw out of a bag of marbles, that is two independent events because they really don't have any influence on each other. So the independent is easy. If you want to know the probability of A and B happening, and we're going to start, I'm going to show this this word a lot, sequential, meaning you want to have something happen and then immediately something else, two separate events. the easiest thing to do is to multiply them. Where you have to do some thinking is you have to think, so you're just going to take the probability of the first event by itself times the probability of the second event. What you have to think about, though, is up here. This means take the probability of the first event times the probability of the second event if you take A away. So you just have to decide, did I take something away and change the total, or did I leave the same and not mess with it? So we'll come back to this 1 minus P none thing. We'll get to that maybe on the next day when I get back, or maybe we'll see how much time we got here. So flipping it over. 3 cards are drawn from an ordinary deck and they are not replaced. Find the probability of these. Getting all 3 jacks. So you want to have an event, an event, and an event. You're going to multiply all these things. The first one is, what's the probability of drawing 1 jack? Well, you've got 4 jacks total out of 52 cards. Probability now, if you do not replace it, that means I take the jack away from the deck. Now there's only 3 in there, and there's 51 cards left. And the second one, or the third option, is you draw another jack, where there are only 2 left now, and there are 50 cards left. Because I did not replace, notice that the top decreased by 1 each time, and the bottom decreased by 1. So I'm going to reduce all these to make my multiplying easier. It's a 1 out of 13. Times, I think that's 1 out of 17, times 1 out of 25. In your calculator, just take 13 times 17 times 25, which is 5,525. So you have a 1 in 5,525 chance of drawing 3 jacks. If you were to get that as a decimal or a percent, that is fine as well. So doing the same thing with getting an ace, a king, and a queen in order. What I want you to do is, I'm going to give you about a 10-second head start here. I want you to try this. Getting an ace, a king, and a queen, setting up what I did here, meaning we got an event, we got another event, and we got one more event. Trying to find out these probabilities. We are still not replacing. Can you give you 10 seconds? So, the probability of getting an ace is a 4 out of 52, because there are 4 aces. Getting a king, there are 4 of those, but because I'm not replacing, there is now 51 cards in the deck. A queen, there are 4 of those, but again, I have to change this bottom number because I took another card away. So these top ones now this time stayed the same, but the bottom decreased by 1 because you're taking 1 out every time. So you end up with a 1 out of 13 times, that does not reduce, which is awesome, times, what's that one going to give you, 2 out of 25? So it's an 8 over, let me multiply that real fast. I got a 16,575. So you can leave it as a reduced fraction, or you can divide by that. And as a percent, oops, it is 0.0004, which isn't very good. Which, if you move the decimal place twice, it's a 0.04% probability. Not very good. So, here's what I want you to do. Same thing as what we've been doing. I want you to try this letter C and letter D. I want somebody to go back to my computer and pause the video right now and try C and D, and I will put the answers up here for you to check when you're done. So pause the video and try C and D at your desk. Continue to pause and kind of check out my work. If not, we are going to move on down the bottom here. We're about done. If 17% of the people in the United States smoke, find the probability of picking 3 people at random, finding that all 3 smoke. Here is your empirical probability. This is dealing more with percentages. So the first probability that you have of smoking is a 17 out of 100, or if you want to write that as 0.17, you can. Times, you want another one and another one. So find the probability of picking 3 people at random and finding that all 3 smoke is 17 out of 100, 17 out of 100, and 17 out of 100. Or you can go 0.17 times, 0.17 times, 0.17, which is, in a calculator, 0.004913. So about 0.49%. Not even quite a half a percent. Same thing down here for 44% of the professors at a 4-year college are female. If you sign up for 5 classes, find the probability that you get all female professors. I would go 0.44 times 0.44 times 0.44, or 0.44 to the 5th, which in a calculator Get mine out here. Going through it very quickly, I got a 0.0164, which is about a 1.64%. Again, if my calculating's off, I apologize. I do not have a regular calculator. I'm using my phone. So that is using empirical probability, using some percentages. Flipping it over. Let's talk this side. Box of 35 computer components has 6 defectives. If you test 2 of these, find the probability that both are fine. Companies actually do use this quite a bit. Let's go maroon. Okay, so you're picking out 2 things. So I'm going to go blank times blank. My job is to figure out top bottom here. Well, what's the probability? The first one works properly. There are 6 defects out of 35. So the good news is this is 35. There are 6 defects, which mean there's 29 that are good. So it's a 29 out of 35. But when I test the second one, obviously I've already taken one of the good ones out. So now there's only 28 left, but there are 34 total. This would be a non-replacement, or this would be a non-replacement because you're taking it out and you're keeping it out. So I'm going to go 29 over 35, 28 times 34, or over 34. Grab a calculator here. So 29 times 28, and 12, all over 35 times 4, 1190. Divide that out. Don't forget, another way to kind of check your work here is none of these should be over 1. There's not a single one of these answers that you should get that should be over 1. They're all going to be between 0 and 1. I get 68.2%, or a 0.682. We okay there? Okay. Right here, same type of thing. 30 students total, 5 made A's. If 3 students are selected at random to do a special project, find the probability that all 3 students make A's. So I got 1, 2, 3 students I'm talking about. I got a 30. I got 5 of them. I got a 5 in 30 chance on the first one. And then I took one out, so now there's a 4 out of 29. And then the next one, there's a 3 out of 28, and so on. I will let you do the calculating here, but you can multiply those out, see what you get. Down here, 23% of the class passed the first and the second. 45% of those that passed the first test also passed the second. Find the person that passed the first. This is going to be this fun game. We want the percent that passed the first. Well, I know that 23%, or 0.23, passed the first and the second. So let me cross this out. So this is past the first and the second. That is equal to the probability that passed the first times the probability that passed the second. That would be the probability that passed. Here, all I'm using the same formula. I'm going to multiply these probabilities. The only thing is now I know what my total is. I know, let me get a different color. I know my total is this 0.23 because it tells me that's how many people passed both. So let's go blue. So instead, I'm going to set this equal to 0.23. 1 second here. Let me check my notes. Hang on. This passed the first. This is what I'm looking for because it says find the percent that passed the first. Percent that passed the first. That's what we're looking for. So what I'm going to do is I'm going to turn this into an X because I don't know what it is. But I know how many passed the second because it said 45% of those that passed the first also passed the second. So this would be kind of like the S or the F/S. This would be kind of the replacement, or in order to, this is dependent on this first one because you have to pass the first to pass the second. So therefore, this is where my 0.45 goes. I'm going to divide these two things out, solve for X, which is my probability that they pass the first. And if you divide those out on a calculator, I get, I think, 51%. Yeah, 51%. This one is the same kind of thing. So what I want you to do, and this one is a little weird, so I'm going to give you some more time, but I want somebody to go back there, pause, and we're going to try this one, and then I think we may call it a day trying this 35%. So pause, try that one, and then I'll put the answer up here. You know what? I decided this is a good one to talk through anyway. We're going to talk through it together. I lied. Don't be mad. I'm only doing this in one take. I'm not redoing it. So, the probability of, we're talking about eating a healthy breakfast and exercising regularly. Find the probability that a person who eats a healthy breakfast exercises regularly. So, we want to know the probability of regularly. So what we're going to set up is we're going to set up the probability of eating healthy and exercising is equal to the probability of eating healthy times the probability of eating healthy and being affected by exercising. So the probability of eating healthy and exercising, it says 18% of adults eat healthy and exercise. So there we go. There's our 0.18. I want to know this probability. Whoop, this should be a healthy. This should be an H. My bad, not an R. This should be an H. So here's where my X goes. Times the probability of eating healthy and exercise right here. We got a 35. Oh, no, this is 35. I was right the first time. Told you I'm not redoing this. This is my 35 because this is 35% of adults eat healthy. Times, this is what I'm trying to find. Person that eats healthy, exercise regularly. I'm trying to find this now. So that's my fault over here. I'm going to divide those things out in a calculator. I get another 51.4%. We may have to take a look at these again the next day. All right, last page, flip it over. This one's going to be involving a tree diagram. This is the probability of at least one, which I don't think I'm going to talk about in this video. I think I'm going to hit that tomorrow morning when I get back. That'll be these two. So, up top. Let's go up top here. Last one I'm going to show you, this involves a tree diagram. Why this one is going to be a little bit weird is because there are all sorts of different types of probabilities. So what I'm going to say is, okay, we want to know the probability that he takes the bus. So I'm going to look at what happens every single day. I'm going to try to use a tree diagram to determine when he takes the bus and when he drives. The evening weather report says there's a 30% chance of rain tomorrow. So what I would say is it's going to rain or it's going to no rain. Of that rain and no rain, there's a 30% chance here, which means there's a 70% chance here that it will not rain. So now when it does rain, it says when it is raining, John takes the bus to work half the time and drives his car the other half. So when it rains, he takes his car 50% of the time, and he takes the bus the other 50%. So I'm going to go 50 here and 50 here. When it is not raining, John takes the bus 25% of the time and drives 75% of the time. So here we go. Here's a car and a bus. He takes the bus 25% of the time. Or no, wait, I'm sorry. Takes the bus, 25% of the time here. 75% of the chance here. So, taking a look at when he will take the bus, I see, according to my tree diagram, I see a bus here, and I see a bus here. So what I'm going to do is I'm going to kind of work my way backwards. Let's grab a different color. Let's go mocha. I'm going to work my way backwards here and say, okay, I'm going to treat this kind of as one event, where the probability that it doesn't rain and he buys is going to be a 0.7 times a 0.25. The probability that it rains and he takes the bus is a 0.3 times a 0.5. I'm going to get two decimals here, and I'm going to add those two things together using my addition rule. So, 0.3 times 0.5 is a 0.15. There's a 15% chance that this event up here happens in yellow. This has a 15%. And down here, 7 times 0.25. We got a 0.175% that this happens, so 17.5%. Add those two things together. Looks like we got about a 32.5% that our buddy John takes the bus tomorrow. So this is how you can use a tree diagram. Down here, I will kind of hopefully get down. Oh, I almost want to do this right now. No, we're gonna take a look at this tomorrow. We'll take a look at this at least one tomorrow right away in the morning when I get back. So hopefully this helped a little bit. I understand there will be some questions. I will be available in the morning. If you want to come see me, please do so. Do the best you can with this assignment. Try to help each other out if you can. And I will see you all tomorrow.